Uh, Good morning, everyone. Today we will start another very interesting topics on the AI. Okay. Remember, in the last two lectures, we talked about the three, what we call the three pillar, main component of AI. They are the artificial neural networks, fuzzy logic, and also genetic algorithm. As I mentioned at the end of the course last week, the main function for the neural network is to provide overall network architecture, okay, for us to, so for example, to forecast the finance or doing the prompt tradings. And so the main function for the neural network itself is infrastructure, okay, for us to do some AI applications. So, for example, forecasting, pattern recognition, expert system, and so on. And the main function for the genetic algorithm is on the what we call optimization, okay, especially in different kind of systems. Say, for example, for our neural networks, there are many parameters, right, and also some weight. So, which means you have some kind of a scheme to do some selections for the best set of parameters. So, for example, on the learning rate, the learning momentums, or how many hidden nodes, okay, we need to use. So normally we can use some kinds of evolution computing method. Say, for example, the genetic algorithm for optimization. So you can see optimization for using GA all the time is a combination with other technology as well. And for the last one is quite interesting, is the fuzzy logic. Fuzzy logic, actually we have two main purposes for using it. One is it can be used in order to falsify some kind of attribute or variable. So, for example, you can falsify the temperature and the relative humidity for the air conditioner, right? Also, you can falsify some, so for example, in finance, you can falsify some parameter. So, for example, for the RSI, the resistance relative strain index, okay, to normally for the RSI, normally we have to classify into three different kinds, right? The bull and the bear, or in between, neutral. So all the time it can be some kind of fuzzy consideration. So by using fuzzy logic, we can falsify this kind of parameters of variable. And another important application for the fuzzy logic is to implement the expert system based on the fuzzy logic. So fuzzy logic itself, it can be used as a component within a big system. So, for example, you build a forecasting system for finance based on the neural networks, and in order to choose the best set of parameters, you are using the GA, right? In order to falsify some variables, so for example, the RSI and the MA, so you are using the fuzzy logic to falsify these parameter first, or the variable first, and then fit into your neural networks. So all the time it can be a kind of integration. But as I mentioned, for the fuzzy logic, it's a bit different. It has the second usage. Standardly, it can be used to build an inference engine using the if-then-else, which means some kind of what I should say is a rule-based system. Okay, just like the example I gave you in the last lecture at the end, how to make use of the fuzzy logic together with some basic financial rules to do some kind of a decision support system. So, for example, when the price drop to which level, you want to do what? Okay, that kind of thing. It can be a kind of fuzzy system. Okay, something like a control system of what we are talking about using applied in the air condition, that sort of thing. So you can see all these kind of AI systems, they are not standalone. Okay, but the question is there any others? Of course, there are many. So today we will talk about the two very important AI tools, what we call the chaos and also fractals. In fact, these two things, in fact, I can tell you that during the course today, they are the same thing, but using different angle to see it. So the formulation are different, but they're talking about the same thing. And I will talk about the basic concept again, and also how it can be used in our daily life. And more important is how to make use of it in the financial engineering, also in our quantum finance. Okay. In fact, for our system using in the quantum finance forecast system, or using in our QFC.organization website every day, what we are doing every day is a combination of a different method, especially on the chaos theory. Okay. So this lecture, I will focus on two things. First, basic concept on these two interesting technologies. Only the basic concept, don't worry. And give you some very simple example. And secondly, tell you how to make use of it, okay, in financial engineering. And then in the next lecture, I will combine chaos theory together with the neural networks to tell you how to build chaotic neural oscillator. Okay. So next we will talk about the last interesting AI topics, the neural oscillator. So today we focus on chaos and fractal first. Normally we can finish this within I think 1.5 hours. Okay, won't be too long, so don't worry. In fact, for my book on quantum finance, it corresponding to the chapter 8. Okay, so if you are reading my books, you can refer to chapter 8, and there are many interesting examples you can explore. In fact, for today, the lecture, for the 2-hour lecture, mainly we focus on the basic concept. So don't worry, okay? I won't go into too deep. But for you to do your own theory project or the research project in the future, in fact, chaos and fractal is a very good example, and very good topics you can try, and also you can explore in your future research. And also, as you can see from my iSpace material, also I have a list of papers, okay, a good journal paper in fact, and so that you can refer to it and do your reference reading, okay. And other thing, remember, okay, and now it's almost week 10, right, something like this, and remember to put more time on your group project and also the term papers, okay. And any problems, just reach me, and also you can ask me during the lecture hours. Most important that you can reach me anytime using WeChat. I will, when I'm free, I will answer your question. Okay. And I think now the WeChat is quite good because you don't need to send email. Okay, because nowadays I simply use email for communication. So most of the time using the WeChat. So if you have any question about the course, and also some technologies. For example, if you want to learn a bit more on chaos theory or fractals, you can ask me. I can give you more reference or directions. Okay. In fact, it's a very good theory project topic. Okay. So that's one thing. So let's start. So today we talk about chaos and fractal. In fact, the first time I learned this, okay, is almost more than 20 years ago, okay, when I'm still working in the Hong Kong Observatory as a forecaster. Okay, at that time, chaos and fractal is a very, what should I say, very in and very niche topics, but very important. Later on, I will tell you why. Because chaos theory is very related to weather forecasting. In fact, it's discovered by a weather forecaster. That is the reason why I'm so interested. And fractal itself, in fact, is another angle of chaos. I will tell you why. And fractal is now very important in finance. In fact, as you can see from the MT4 platform, there is a financial indicator, theoretical indicator called fractals. Okay, I will show you in my PowerPoint. And although it's very simple, but it shows you how fractal can be used in finance. In fact, it's very important. As far as I know, more than many years, more than 30 years. Okay. At the beginning of fractal, in fact, is what should I say? The R&D is mainly focused in US, mainly in some important top university, example MIT and also Princeton. Okay, especially in MIT, they do quite a lot of research on finance. Okay, supported by some fund house. And basically, they are using chaos and fractals. Okay, that's why for my book, I think it's quite good to use the chapters to tell all the readers how important this technology is. This is one reason. The other reason is because for my forecasting system, I already use some chaos theory. So that's why I need separate chapters to do some, introductions on chaos theory, so that all the readers and students have some basic ideas. But of course, it's just basic introduction, because in some top university, so for example MIT, okay, in Singapore University also they have separate course on chaos and fractals. It's a 40-week course for again 5-year student or master degree student. Or of course they are more in depth into the technologies. Okay, but of course if you want to do it as a kind of a Friday project or your future master degree project, come to me, okay, or you can reach me. I can give you more material, because I got a lot of material on that. Okay, so don't worry. Just introduction. So again, we talk about the same things, the financial market, right, and what we call the duality behavior. Sometimes it is a wave patterns, and sometimes we treat it as some numbers. Okay, in fact, chaos and fractal also the same thing. Okay. First, in the previous lecture, we talked about the concept on quantum theory. Okay, and we talked about the fancy ideas on the wave and particle duality theory, right? And my favorite, the Schrödinger equations. In fact, as I mentioned, the Schrödinger equation is the most important equation, as far as I know, in the science world, and also invented in 1925, almost 100 years, without any change. And still, people like me investigating on that. But different is, now we have some very powerful computer, and even, what should we say, the quantum computers to make use of it. So it become more than fancy. So in fact, the modern mathematics, computation physics, okay, also have that kind of thing. But we put it in another way. We talk about the two-phase concept, the chaos and the fractals. Okay, one talk about the chaotic behavior of many things. Okay, you can see the butterfly effect, and the other talk about some very interesting repeating patterns. Okay, very interesting, all these topics. In fact, when I'm working in broad observatory at that time in Hong Kong for weather forecasting, whenever I have time, I spend time to reading books on chaos and fractal, because as a physics and computer science student, it's very interesting topics. And of course, because it can be used on forecasting, that's why I'm so interested. Okay. So more important, these two mathematical models have important implications on finance and AI. That's why it's so important. In fact, it's a very important branch in the computational intelligence, the CI. Okay, and as a matter of fact, it is a very important and niche topics on future AI as well. And I'll tell you why later on. So as mentioned in the beginning of the chapters, okay, we all know the financial market itself exists in two patterns. Okay, either as particle, the price, and second, a global effect as a kind of pattern. That's true. In fact, it's already occur every day. Okay, so all people believe. The only thing is, can you do the modeling? Okay, once you can do the modeling, you have the chance to do some prediction, right? So all the time we are doing that. I can tell you that for 100 years, many years. So applying some numerical computational technique. Okay, so in the past almost 10 lectures, we talk about how to quantize, okay, them into what we call the quantum energy level, what we call the quantum price level. Okay, so we have to do something, at least, right? So, which means we have some chance for us to build some bridge, okay, between some quantitative figures and some overall phenomena like the energy level. So we have built some bridge on that, okay, and make use of it, okay, in computational finance, and of course what we call the quantum finance. And the most important part is we don't need to, what should I say, to handle so very sophisticated path integral problem, because for me it's too complex, and for the computer it's too heavy loading. So what we can do is that to simulate into some global phenomenon like the price level, so that the trader all over the world can make use of it, okay, without any deep thinkings on how complex it is. Okay, in fact, it's not too difficult. Just like as I always say, just like every day you wake up and you see the weather forecast, and you don't need to think about how to do forecast, right? You only need to do how to make use of the forecast itself. So that is important. Okay. So of course the answer is yes. Okay. In finance, we have a very similar concept, what we call chaos and fractals. So let's talk about the first topic, chaos theory. I don't know whether it is totally 100% true or not, but as far as I know, all the research students, okay, when they learn chaos and fractals, all the time they learn chaos theory first, and then fractals. Okay, if somebody tell me that they learn the fractal first, it's quite funny, because chaos theory all the time should be the first thing you learn first, because it's quite obvious, this phenomenon, because the first phenomenon is on weather forecasting. I will tell you now. Okay. World of nonlinear dynamics. As I mentioned, if you have learned my course in the year 1 or 2, I forget, on the linear algebra, and I tell all the students, okay, every year, linear algebra is very important. It tells you one thing, right? Matrix. And the role of linear algebra, okay, or linear dynamics. But the world is not linear. So, for example, as I always say, if you have some experience in driving a car, and all the time when you go out, okay, the car limit should be 14 or 15 or 15, I don't know. Okay, in here. In Hong Kong, it's about 60 km per hour. So all the time, in order to keep you at a constant speed, okay, you have to press, okay, the brake or the oil alternatively, right? So, but if you try to plot the motion of the car, so although it keep a so-called a normal speed all the time, but in fact it's not, right? All the time they are non-linear, go up and go down, go up and go down, just like the financial market. So what I want to say is the reason why we learn linear algebra is because at the beginning when you learn something simple. But solve it, the whole world is not linear. They are very, very non-linear. Non-linear means that it cannot be formulated by some linear equations. So we call this non-linear. Okay. So what we call the butterfly effect and the chaos theory. I will tell you a bit more. So what is the nature of the world? Many people, okay, in different areas, as I always say, ranging from philosophy to computer science and AI, all the philosophers and scientists are working about this all the time. Especially now with once we have so many VR, virtual reality film. So for example, the Matrix, okay, and all the others. So we have different theory now. So for example, the simulation theory. I'll tell you a bit more later, okay, when you talk about the other topics. So nowadays we have some cross link between different disciplines, okay, and we raise a lot of questions on how the world, okay, what is the mechanism of the world dynamics. Dynamic means how all the things inside the physical world work. Is there any relationship? That is very important. As I mentioned all the time and learned by all the previous professors, okay, from different universities, if we don't believe, okay, there is some relationship between different things, or between a single thing in a time series, nothing we can do, right? So we force, as I always say, we force to believe there is some kind of relationship. And as a computer scientist like me, doing weather forecast, we don't believe in one thing, what we call random. As first time I learned the quantum mechanics, one of the objectives is this. There is one phenomenon for us is very, very puzzling. Is what we call the Bionic Motion, right? The Bionic Motion is about some air smoke particle that have what we call the zigzag motion, okay, all the time. And a long time ago, many scientists working about this, and some of them, there are two kind of people, okay. For the people working in statistics, they believe that kind of motion are totally random. In fact, they are using the Bionic motion to classify what is random. And because they are so random, so nothing we can do analytically. So they build a lot of what we call statistical model, okay, to do some statistics. Statistics means that you cannot exactly know and predict anything. So what you can do is to calculate the average, calculate the standard deviation, no more. But as I always say, statistics is good to give you some ideas, but it have one problem. The problem is, no matter how accurate, because there is no accurate in statistics, as I always say, because all the time there's some, what should I say, the confidence level. So I should put in this. No matter how good your statistical model is, you have no way to forecast, because your model doesn't allow you to do so, because the model tells you that everything is random, right? So there is another branch of scientists, including me, believe all the things are related. But they are so chaotic, so that it seems to be random. It seems to be random, which means it's not random. And why it's so chaotic? Because there are some property. First, they are very complex and nonlinear equations. I will show you one very, very simple one later on, the logistic equation. And second, the motion of the particle or the object inside this model are very sensitive to what we call initial condition. Just like weather. So based on this, in 1960 or 70 something, okay, there is a scientist called Lorenz, very important, Lorenz, this guy. At that time, is MIT research, okay, scientist working on, like me, on weather forecasting, and like me, using 7 physical equations, like the fluid dynamic equation, the fluid dynamic, and also the thermodynamic equation, and Newton's law of motion, 7 equations to predict weathers. But in order to predict weather, everyone knows we need the initial condition, right? The air temperature and the pressure and the wind speed and direction for every single grid point, so that you can forecast the future 7 to 12 hours. And one day, this guy, maybe like me, okay, haven't slept for a whole night, and when they key in the, I don't know why, he key in the data, maybe do some data processing, I don't know what. But I'm doing that, I'm using purely computer. And accidentally, he make some mistake in keying the initial data. Okay, then when the mistake is very small, just the deviation in the decimal point 6 or 7 or beyond this. Okay, and he discovered one very important thing. Although the error for the data input is so small, okay, insignificant, what we call, but the forecast result in the future 3 days are totally different. Very surprising, because in terms of classical computational science, all the what we call system error should be proportional to your precision, right? But we discovered one thing at that time is, for some very special system, what we call chaotic system nowadays, this system is very funny. Even a very, very small deviation for the original data the whole forecast result are totally different. So we call this sensitivity to initial condition. In fact, it's the #1 characteristic on the chaos system. And that fundamental characteristic tell us one important thing. All the things we seem random is not random, but is very sensitive to initial condition. That's what I'm saying. Okay. I remember when long time ago I see the film Jurassic Park. There are scientists, okay, also talk about chaos theory. The demonstration is like this. They put a drop of water onto your hand. Okay, just like me. And show you one thing. So how did this drop of wet water go on your skin, on your hand? So it seems to be random, right? Because what? Because it depends on the size of your water drop. It depends on the speed you are falling. It depends on the temperature of your skin, or also the moisture on your skin. But it's not random. Difficult to predict, but not random. So we call this kind of randomness, we call this deterministic chaos, which means they seem to be chaotic, but they are deterministic. Deterministic means once you know the initial condition, you know the future. Very, very interesting, right? So other that many people, including me, of course, spend a lot of time on that kind of system. And the #1 application, of course, is on weather forecasting. So that's why, as many people see all the time, are doing forecasting and start with weather forecasting. Okay. Of course, not only weather forecasting, it's also related to the forecasting the thunderstorm, forecasting the lightning, forecasting the windstorm, and forecasting earthquake. In fact, the earthquake is the most, as I always say, is the most important but difficult one. Very difficult because it's related to so many things. You can imagine. Okay, not easy, but possible. Okay. Okay, I'll continue. So we talk about many things. The falling of any object. So Newton's law of motion. The formation of the dynamic black hole. Okay, Einstein theory of general relativity. Because at that time in 1980 something, all the science students, including me, fancy about two things: quantum mechanics, okay, and also the general relativity. So these are two major topics until now, of course. Okay. And dynamics for subatomic particle. Okay, the quantum mechanics, very important. In fact, I can tell you that without this technology, we don't have our plasma TV. We don't have our latest development in our iPhone and Android phone. I heard, so-called solid-state physics, because all the solid-state physics talk about the subatomic world. So of course there's a limitation. As many people ask, is there any limitation for the advance of technology? Of course we have, but we still have a long way to go. Don't worry. Okay, until we die, it's still ongoing. It can be. Okay, so don't worry about it. And the formation and dynamics on anything like the tornado, the tropical cyclones, and so on and so on. Okay, we are all doing this. I can tell you. So, for example, in the U.S., we have the NOAA, and also the TC centers in Florida, okay, doing that kind of prediction. Because weather prediction is a global, global collaborations over well, including China, of course, okay, and very important organization. Because you can imagine we have to share all the data. Because you cannot have a single country to collect all those meteorological information, right? So as a long time ago, maybe after the Second World War, I think, we are all collide together to do the first development thing on the GPS positioning and also on the weather predictions. These are all free of charge collaborations, okay? And each country donate their data on weather prediction because it's very important related to the protection of people and also to avoid some casualty. It's very important. Okay, but difficult, of course. Say, for example, many people ask about tornado. Okay, as you can see, tornado is not so popular in here, but it's popular in Florida, in U.S. The central, mainly because of the the territory formations. So the tornado centers in here try the best to do the forecast within 1 or 2 hours. Okay, they cannot do very long-term forecast, but within 1 or 2 hours is good enough because you can find a shelter to save yourself. Okay, so people doing that all the time. So they all the time have the what we call the tornado warning and the fluctuation of stock. Okay, so many things. And the funny thing is that if you spend sufficient time on that like me for more than 30 years, you will know one thing. They are all connected. They are totally connected and related. Whether it can be, just like Einstein saying, it can be unified by one single equation, I don't know. But one thing I do know is that they are all related. So that is what is we're talking about in chaos theory. Everything is related, so that we have the butterfly effect, right? In fact, the butterfly effect is talked about in two. There are two versions, I should say. First version is long time ago in 1970 something. Is by Lorenz. Okay, my version is from Lorenz. It's Lorenz in the second conference on his chaos model, Lorenz equation. Tell the people one analog is the chaos theory is talk about is when something happen long distance. So example is a butterfly. Okay, try to find the wing in Amazon. Okay, version 1. Okay, and because of the chaotic effect, okay, it can affect a far location in Florida. That will cause a tornado. Version number 1. Version number 2. Version number 2 is similar. Okay, again is the butterfly in the wing, and there's earthquake in the South America. So I think the first one is correct because as far as I heard, it's the first version. But then they are talking about the same thing. Some very minor thing happens in a long way because of the chain reactions. Okay, because the sensitivity to initial condition, remember that. So it will affect something very global a long way ago. Okay, as a matter of time, of course. So we call this chaos theory. It's just an analog, of course. And the other explanation for the butterfly effect is what you can see in this diagram. This is called the Lorenz patterns. Okay. The chaotic patterns, and as you can see, this pattern is just like butterfly filling the wings, right? So that's why what I can say is that's why Lorenz think about the butterfly effect because of this pattern, but not because of this pattern. Okay, you have the butterfly effect. It's just what should I say, analog. Okay, so that you have some ideas, and of course the last thing is calculation. 因果关系, okay, cause and effect. It's a matter of time. But that one is quite natural, right? So, say for example, when you drop mouse, so it will fall to the desk, okay, or break down. The cause is you drop the mouse. The effect is you drop, okay, and you hit the desk, right? Yeah, of course. But again, later on, you will find that if you believe in what Einstein says, okay, all the times, in fact, is a kind of artificial creation by the mind of a human. So, okay, so many things can happen in heaven. Okay, once you have more deep investigation on everything, okay, the way you see the world is totally different. So, hopefully, is after this lecture, you have a new way of thinking of how the world works. Okay, and what I should do and I can do is to give you more possibility. Okay, how the world look like and how you can do on your R&D or on your IT career. Okay, many things, and your fate. So you can see the number going on, it becomes more and more difficult. Calculation is difficult, right? Your face, of course, very difficult. They are all related, right? But we believe there is a pattern. And the pattern, or what we mean by pattern is that they will repeating and repeating. We call this pattern, right? So only based on one thing, is everything is cause effect linked up together in two domains. One, in timeless domain between object within the same time frame. Second is the life of the object within the whole line of time. That part is very funny because later on you will know, if you learn more about physics or computer science, you will learn time itself is a very funny kind of thing. In fact, if you have more concept of finance, you will also know that time itself is a very funny thing. It's quantized in finance, right? We have the daily, weekly, hourly, 4 hourly. Okay, and every time step, the time frame, you take a look on the market, they're different. So what is the truth of the time? Well, you don't know in fact. But of course, what we want to know is to build a model that you can forecast the pattern, of course. So that's why we are working so hard on that, right? And your future. So you can see chaos theory is talking about that kind of thing. So that's why it's so, what should I say, it's so interesting for many top students in many Western countries especially, okay, on that kind of calculation. But because nowadays AI becomes so popular overall, including here, so I think the chaos theory will become more and more popular in here as well, okay, because chaos theory is good on one thing, is to model something super complex, like the financial market, or the weather, or the earthquake, or anything. Okay, but if you ask me, have you ever used chaos theory to predict your own future? I never, because I don't think I can do that. And I also don't think all kinds of prediction technique you have heard about. Okay, there are some statistics all the time. Okay, for your fate. And statistics, as I always say, is that there is no true and false. It's just probability. Probability is something I'm not very confident with because I can't predict future with probability. It's just a probability. So, for example, if someone tells you you have a very low chance to win, okay, $1 million draw, okay, lottery, but it doesn't mean you won't have the chance, right? You don't know. It's just a chance. Okay, so you cannot use it to do some more detailed prediction, but you can use it as a kind of averaging and also the what they call the statistical analysis. Okay, so there are two kind of things. Okay. So in fact, chaos theory is the study of all those kind of dynamics. So you can see dynamics all the time can be very solid kind of thing, or can be very what should I say, is a very non-physical kind of thing. Okay, even, so for example, what you are now thinking about, your thoughts, can be a kind of chaotic dynamics. Okay, so don't bother yourself into something only physical or non-physical. Everything is correlated. Okay, so many things you can learn, of course. So in other words, if one wants to explore the nature of dynamics, governing matches, and notion in the universe, one must enter the role of chaos theory. So the battle between two roles, deterministic and probabilistic. Oh, my favorite. So one may ask, as everything that happens in the world is highly dynamic or chaotic, so does it mean that chaos theory is the study of probability? The answer is no. True is that chaos theory has the basis that is totally different from that of probability. Although chaos theory is the study of the world dynamics, it's not the world of uncertainty as a matter of chance. So we have to learn about what is determinism rather than probabilism. So chaos theory is trying to build a dynamical formulation or equation, what should I say? Maybe one or a set of equations. Just like the Lorenz equation is a free equation. Very simple free equation. I will show you. And it can model some very chaotic thing. Okay, so it is deterministic in some sense. So, so the first thing is whether we can find all this chaotic motion is another question, right? But what we believe in, we can find that, or that kind of set of equations exists in the world. That is important. So in fact, the formal name for chaos is many people, including me, will call this the deterministic chaos. Deterministic means you can determine. Okay, it's not undetermined. And of course, it's not random. Okay, or probabilistic. So in terms of mathematical formulations, okay, we have two ways to present that for any dynamics. It can be discrete format, or it can be continuous as a continuity equations. They are the same. As I always say, how can you think about that? So, for example, when there is a particle moving in here from one to another, so you see it's continuous, right? But when you put a space, so a plane across this, so you can only see the point, right? And all these points seem to be very chaotic, right? Do you know what I'm saying? So, for example, when I'll say again, in a 3D world, when there is some motion of an air particle, just like the Bionic motion, okay. And sorry to tell you that you only have a plane of observation, like this. So when you move one, you can only see the dot, right? And then you will tell me, oh, this dot is so random. But if you reshape your dimension into 3 dimensions and you see the curve, and you see the whole dynamic. Do you know what I'm saying? Which means, in one way, you think that they are random. It's because of the dimension not enough. If you have sufficient dimension to change the perspective, and you will learn the dynamics. Which means, for something that seems to be random, it exists a set of equations, we believe, okay, that you can model them all, and they are deterministic. Because once you can model, you can predict, right? What I'm saying is very simple. When there is a motion for the particle, so this is the 10 days before, 9 days before, and then last day, today. Once you know the dynamics, of course you will know the future. So why Einstein saying is that because of this, everything is determinate. So his theory, many before, after he proposed the relativity theory, he say very funny thing. All the things happen in the different series time, they should be happen at the same time. You just human link up them all in time frame. So what he's saying is time should be quite artificial in some sense. I believe that, I don't know. Okay, later on I will tell you why in the next lecture maybe. Okay. Continue. Chaotic flow and chaotic map. That one. Yeah, that's one. So one important idea of chaos theory is that kind of thing. Is what I'm saying is chaotic flow is the continuous motion for anything, okay, in any dimension, and chaotic map is the what we call the cross section of it, what we call in reduced dimensions. So you can see if you just take a look on the whole chaotic flow, they are continuous, right? And you can model them. But when you talk about all those points, they are chaotic. But in fact, they are not chaotic. That is what we are looking for. If you are genius enough, you know what I'm saying. Yes. The financial pattern seems to be very chaotic. But if you are genius enough to create a set of equation, you can have another perspective to see that fluctuation, and you know they are not chaotic. So that is our R&D direction. Okay. But of course, to do that, you will have to spend a lot of time to try to search for that set of equation. Right. For me, it's spending more than 10 years to have some new idea all the time. Okay, it's very time consuming. Oh, you search all the time, it's very consuming. So, a quick view of chaos theory. Okay, chaotic phenomena. So I show you my favorite Lorenz equations. Lorenz equation proposed by Lorenz, of course, is 63, sorry. Okay. And before, okay, 963, no. And at that time is after the Civil War, of course, at the beginning of computer history. And also the most important part is at that time, all the major universities in US, okay, working around on some very, very basic thing. So, for example, on weather forecasting. Okay, so because we believe weather forecasting is very important. It can, once you can do so, it avoids many casualties. Not imminent casualty, because as you know, in many countries, including US and here, okay, sometime all the time we have the hurricanes or the typhoon that cause a lot of casualty. So if you can predict that, of course you can save the life, because you can tell people, okay, to get around. As you know, in the past few years, US near to Florida, they have many super hurricanes. And the hurricane is so super that I can tell you last year, right? The super hurricanes, their intensity is 10 times stronger than 20 years before. Mainly because of the world have over pollutions, okay, and the typhoon and the hurricane become stronger and stronger. So that's why weather forecasting nowadays becomes so important, because you can save lives. At that time, it's because of the weather forecasting. So you tell people at least 3 days. I remember. Okay, at that time I'm quite serious on taking a look on that. Okay, and they can remind, and not remind is to force people to leave. Okay, Florida. In fact, Florida is very big. It's a coastal area especially, okay, 3 days before the hurricane comes. Otherwise, there will be a lot of casualty. So that's why for summertime they are so serious about that. Okay. So what Lorenz talked about is the 3 basic equations, okay, to illustrate to people how to model weather by using 3 simple equations. And this butterfly effect chart is the 3-dimension plot for the Lorenz equation. Okay, so just these 3 equations tell you a lot of things. Okay, they are simple, but the phenomenon is very chaotic. Chaotic means it seems to be very random. It seems to be random when you just take cross sections, but in fact it's not random. Once you know the initial condition. So initial condition is very important. Okay. So you may ask, how can they get the initial condition for the weather observation? Very simple, I can tell you, and very dummy. It's all for the world. We all lab together, and we cut the whole world into what we call grid. Okay. So, for example, in China, so we corresponding to grid in China. So every 6 hours, we send a balloon from the ground to upper air, and with all the readings. And you can imagine the whole world doing this at the same time. We can collect the information. These are all the initial conditions up to now. But of course, now is maybe replaced by some robot. I don't know. Okay, but at our time, my time in 1980 something, because Hong Kong is also one of the grid points, and I have the chance to release the air balloon. Okay, every day, 3 times a day. So, dummy but important. Okay. So these equations are based on fundamental Strong's equation of fluid dynamics, and also on the thermodynamic equation as well. Okay. In fact, the whole the model for weather is very simple. The whole logic, I'm not kidding, is we have weather because of 2 things. First, we have the sun that heat up the atmosphere, right? And we have the earth that are spinning. So one is spin, you can imagine. The air will move in terms of relativity, right? Because when you spin, the air doesn't spin. So the wind will happen because you are spinning. And because the sun is shining on it, so that some part will be hotter than the other. So that we have low pressure and high pressure. So that we have wind motion. Once you have the air motion, we will have wind. Once we have wind, the pressure will be changed. Once the pressure will change, we will change the RH and the temperature. Okay. So of course it's not so simple, but the basic formulation is something like this. Okay. And from 1960 something up to now, we are using this method to forecast weather all over the world. But of course, nowadays the computer are more powerful, so that it become more accurate. You may ask how accurate it is. As far as I know, in summertime, the accuracy is more for temperature over 90%. Winter is somewhat in that because winter we have the cold surge, right? But for summer it's very stable. You can imagine in summer in Hong Kong all the time in summertime should be 28 to 35 degrees. Now should be around 16 degrees to 25 degrees. Okay, but of course a computer do it another way around. Very accurate. The most difficult is hurricane, of course, because hurricane is a very low class, right? Very low class and super difficult to predict. But we still can do so. Nowadays. And also we have calculation the accuracy as well. So everything now become possible as far as I know. Once we have very powerful computers. So it's possible. And also they are all facts. Okay. Characteristic. There are some characteristics of a chaotic system. First, sensitive to initial condition. Okay, my favorite, which means everything can be predicted, provided that you have the initial observation and must be accurate. So again, it is a philosophical question. What is mean by accurate? What is mean by accurate? So, example for weather predictions, accurate means your observation is accurate. So you may ask a philosophical question. What is mean by accurate observation? Users say accurate observation is so for example you have to measure the wind speed and direction and the temperature, which means your measuring equipment should be accurate. Again, and a philosophical question. Why you say your machine is accurate? In fact, you don't know either. You imagine. Just like how can you say your timing machine, your watch is accurate? Or say, because it's synchronized to an atomic clock. And you may ask, why an atomic clock is accurate? In fact, you don't know either. But something you know. We have something very close to accurate. That's true. Which means if you are a genius, you will know what I'm saying. Just like, in fact, it's not exactly is uncertainty principle. You can't 100% accurate, but you can be very close to 100%. So what we're saying is everything is chaotic because you have no 100% sure your initial condition is correct, right? Second is the highly nonlinear but deterministic in nature, which means you have something to do. That's why we have daily forecast, right? Otherwise, we don't have it. So for example, if your model is statistical models, of course you cannot forecast anything, right? Because people are not interested in probability, interested in some actual figures, right? The existence of purification point that needs to care. I will talk about this later on. That is the important concept. Okay, but I need a chart. Okay, okay. So, by first. Okay, there is some what we call the purification point. Very important concept. And the existence of cell similarity. And Fractals. So you can see. Chaos theory, one of the characteristics, in fact, is Fractals. Fractals and cell similarity is talking about the same thing, which means the pattern repeats itself again and again. That theory, I come across this is after 1 year I learned chaos theory. At the end of the chapters, I talk about cell similarity, and then I know what they talk about. Because it's just a cell formula. And this formula, in fact, can generate patterns, repeat and repeat. Okay, I will show you later. Very interesting. And very important, of course. Okay, so some characteristics. Sensitive to initial condition. That's good. That is a simple pendulum. using two plastic, okay, and linked up by a simple joint. And again, it seems to be very random. In fact, it's not. It depends on the initial condition. What is that? Here's under this two. It's the initial position when you place this configuration. Okay. The funny thing is, you will think it's chaotic, right? In fact, it's not. In fact, it's not. So all the time it can be different, because all the time just a minor deviation. So for example, every time you think you are stuck with this, in fact they are different, because even though I can tell you that even though the configuration are the same, but the air pressure, you can imagine, because it's not vacuum, the air pressure in different time. So it's just like I open a fan, in different time they are different. So the falling speed will be different. Which means even though it seems to be every time the initial configuration are the same, so the whole pattern are pretty different, but they are deterministic. Okay, so initial property. So of course the butterfly effect, right? So layman term, and in fact the tool is this one, Florida tornado related to a butterfly in Amazon. And any place, okay, but it doesn't mean that it's actually negative. It just means that, okay, everything is connected or related. That's it, okay. And you can't have 100% sure for anything, but it doesn't mean that you cannot do anything. That is important, okay. Highly nonlinear but deterministic, okay. So even though there is slight difference in initial condition, that can extremely different, but all the systems are deterministic once you have a very good initial oscillation, right? So it's the two-way process. So deterministic means that the equal cause have equal effect. Cause and effect. So from another viewpoint, the equal effect have equal cause. So you have to think about that. For me, I think about that for a few day and night for these two causes. So equal cause have equal effect means predictability, right? That is, given E1 is the effect of cause C1, if there is an other cause C2 that come up to C1, so what you are doing, you can predict C2 will have an effect equal to E1. Maybe not, but very high chance, of course. Right? So we call this prediction. So equal effect have the equal cause mean reversibility. Not very few people think about that. So think about that. That is, we're given E2 and E1, there are two equal effects. With E1 caused by C1, then we can say the cause of C2 equal to C1 of C2. Think about that. Okay. So there are some very basic logic behind. Okay. Purification Theorem. That is interesting. So one may wonder whether only complex nonlinear equation like the Lorenz equation have chaotic effect. Of course not. Many simple equations, in fact, can be very chaotic. Okay, just like the logistic equation. This one, just this one, is the x of the t times 1 time step, which means the next time step, equal to r is the real number, xt 1 minus xt. Very simple, right? But highly chaotic. Just show you. Yeah. So for any book on chaos theory, we will show you this purification diagram, right? What is called purification is like this. This chart plot the growth rate R as a function of the population. Okay, the x. So you can see the whole pattern for these equations is dependent on R. And this graph plot from R from 0 to 4. It can be anything, of course. So for this, you can see it belongs to a different part. For the first part, from 0 to 1.0 and R, it is all 0. When it is 1, the R is 1, up to, let me see, up to 3 point something, I can't remember. Okay, it still is a nonlinear equation, 1-to-1 corresponding, right, for x. But when it is after 3 point something, it will have 2 possible results. We call this beautification. And then when it goes to 3.5, in fact 3.4 something, I remember. Okay, it will, each of these will have another smaller beautification. Now you can see this one is the smaller pattern of this one. In fact, the pattern is repeating itself again and again. So condensed that you can't see the result, but they are all repeating itself again and again. So it's just to repeat the pattern again and again. Between me, the phenomenon becomes more and more chaotic because there are more and more possibility occur. But every possibility can be determined physically. We call this the purification point of repeat. Okay, replication. Very important concept. So for a periodic stage to a chaotic stage, such as the dramatic change in the dynamics of the logistic map increasing from 3.5 to 4, which means this, is so condensed that it seems to be highly chaotic. Highly chaotic means it can be any numbers between this range. Okay, in fact, they are deterministic. So this pattern is so important because of two things. First, very simple equation, right? Simple equation. But it shows you one important thing is what? So simple nonlinear system can become chaotic by changing the parameters. That is very important because in the old days, for the past 100 years, okay, from Newton up to 1967, we all believe that a parameter in an equation only change small things. But this chaotic equation tells you one important thing. Change in the nonlinear equation for the parameters, it can change the whole dynamic from non-chaotic to chaotic, which means the parameter is very important. And after in the next lecture, when I talk about our chaotic neural network, I'll tell you a very good examples. Okay, to search for the best parameters that change your nonlinear equation into a chaotic equation to model some highly chaotic phenomena, the chaotic neural networks. Okay. And applications. So many applications: consumer electronics, computer system, healthcare, life science, engineer, business, finance. Oh, many. Okay. You can see from 1970 something up to now. Okay. In fact, there are many applications. Again, like the air conditioner, because what should I say is many systems is especially the home appliances. Chaos theory is very important. Say, for example, inside a cooker or a oven, okay, a heaters. Okay, we all believe that when we have some fan inside it, okay, we call this conventional circulation. So when we do that, we create some chaotic motion, and the heating effect will be more effective to cook things. Okay, and the texture for the food is better. Many new often have that kind of functions. Okay, simple but using chaos theory, and there are many, right? So I don't go through one by one. Of course, if you are interested in chaos theory, you can ask me. I will provide you more literature and also some easy understanding papers so that you have more understanding. Okay. So, chaos theory and Higgs's uncertainty principle. As mentioned, remember our interesting uncertainty principle. Okay, and we have already talked about this related to fuzzy logic, right? In fact, as you can see, they're also very related to chaos theory. In fact, what I always say is chaos theory, you can say, is a kind of new perspective to see the old problems. But the good thing is the formulations. The formulation all the time is not too difficult. So you can see So at the very beginning, okay, we have we call it random, right? Uncertain and random. And now we have the quantum theory to give you the uncertainty principle, but it's only a principle. Principle means difficult for you to do some actual calculation and do something very solid, right? And then we have the fuzzy logic. Fuzzy logic will be using fuzzy falsifications to turn around the question into some model or express system. And now I told you that kind of thing can also be done by using a set of nonlinear equations, and you choose the best set of parameters so that it becomes very chaotic to model your actual system. So you can say it is a new tricks or new tools to solve the old problem. Yeah, that's what we are saying. But the more important thing is now people have some more deep research on how these three things are related. Chaos theory, fuzzy logic, and uncertainty principle. Okay, there are some connections. So there are some mathematicians or computational scientists working on this. Okay, again, if you want to know more, you can ask me. I can give you some paper on that. So the last one is on fractals. Fractals, again, in fact, it's not difficult and super interesting. The fractal, the idea I can tell you that is come from this chart, the Beautification Diagram. Because when you see this chart, you see all the pattern will repeat it again, again, and again. Okay, and then repeating meaning that the pattern itself will repeating itself and become more and more frequent. And then we call this cell similarities. And then we come into what we call fractals. So, history. The study of cell similarity, in fact, is not a new thing. In fact, from 1960 something, we already have scientists, philosophers, in fact, okay, mathematicians, talk about this kind of thing, repeating or recursive similarity. And in 1872, Crow Restaurants, okay, present the first definition of function that can repeat itself. And in fact, we don't have the name called fractal until 1983. Okay, so 100 years before that, okay, we have the cancer set. Okay, in fact, it's the first kind of a fractal. And fractal become more and more phenomena in the early 90s. And then, the snowflake, have you seen that? The snowflake is a very simple equation, but it starts with a triangle. And then, by doing that, okay, it can generate a very complex snowflake. In fact, I can tell you that a snowflake is something like this. True snowflake, I think. The crystallizations. In fact, it starts with a simple triangle, and then repeating itself. You can see repeating itself. Very simple, right? But highly chaotic. Chaotic meaning that this pattern, in fact, can be generated by a set of equations, and that equation is chaotic. So do you know what I'm saying? Which means, if you only take a look on the equations, okay, it is chaotic. If you generate this equation as a pattern, it becomes fractal. So very similar feeling, right? So first, they're the same thing. Second, they're different in terms of perspective. Which means, if you consider it as a set of equations and dynamic, okay, they are chaos equations. If you consider that as a 2D pattern, they are fractal. In fact, they're the same thing. Right? So, and then the 19th century, there's another one called Julia fractals, also very important one. And not until 1967, very important, okay, Mantelbrook, write a very important journal articles called How Long the Coast of Britain, and then coined the word fractals, and then published a very important book called Fractals, Geometry Between Dimensions. In fact, one of the best-selling of the fractal book all over the history of time. after he published the book. Okay, very important book. Not difficult. You can download it or buy it from Amazon. Okay, very important books, and tell you many phenomena on fractals. Very simple, in fact. And of course, if you're using the MATLAB and also many software, they also have the fractal toolkit for you to do some experiment. Okay. In fact, this experiment you can see for the snowflake are generated from MATLAB. Okay. Then browse that. That one. So it seems to be very chaotic. In fact, they generate by a simple self-equation. Cell similarity, non-differential, fractal dimension, 1 to many, many to 1. 4 properties. The material set is a set of value C in the complex plane for which the orbit of C0 equal to 0 and the iteration of quadratic map. Okay, generated by this equation. So if your mathematics is good, you can generate it by yourself. But if not, you can call the MATLAB toolkit. They have the material set. Okay, just generate by this simple equation. You can have something like this. Repeat it. Okay. So you can do that. Okay, and highly recommend if you have time, you can make use of the MATLAB or other mathematical toolkits to generate. Of course, you can write the code, but no one do that now. Okay, because you have the toolkit to do so. So you can see that pattern. The funny thing is it never ends, because when you zoom, it becomes more and more repeating patterns, which means you cannot see the edge. That's why for the very famous movie like the Star Wars, okay, all the landscape, I'll show you, are generated by fractal equation. So that no matter how close you zoom the picture, you cannot see the pixel because they are repeating itself. Right? You can't. All the time the pattern are repeated again and again. In fact, landscape is something like this. I tell you. So this yeah, that is the important concept bring up by Mandelbrot in his long the course of the Britain. The product is very funny. Is so if you have learned geometry, you know how to calculate the parameters for islands. Okay, so you are using a stick or a string. Okay, this paper tell you one funny thing is if you change the unit, which means the length of your fundamental measuring ruler, okay, in different length, the parameters are different. They're different. So that's true, I tell you. Which means the smaller your ruler is, okay, the longer the parameters, and it never ends. In fact, coastal measurement is a very typical fractal phenomenon, what we call. So you can see how people solve this problem after that is if you open a map atlas, you will see when the MATLAB say draw the map, it will give you the dimension, the unit, or it based on 1 what should I say? 1 0 equal to 100 kilometer dimension, which means every time when we now draw a map, we will tell people what kind of ruler we are using. So that's all the problem. So which means that there is no exact solution, but all depends on your measurement method. Okay, and it can be any length for the parameters. Okay, so after the publish, so that's why this paper is so important. It depends on your yardstick. Okay, that's right. So it can be anything, of course. Fractal dimension. Fractal dimension is a very funny thing. I think if you are the first time you heard about this, you have to think about this for 1 or 2 days. It's the dimension we are now seeing the whole world. Okay, 1 dimension, 2 dimension, 3 dimension is only mathematically true. But the funny thing is technically, okay, we can have a middle dimension, which means we can have dimension between 3 to 4 or 2 to 3. Because dimension is just a calculation. So you can take a look on this calculation. And the calculation is not difficult to calculate n, okay, and also the d, the dimensions. In fact, you can calculate the dimension, which means once you can calculate, you can have non-exact dimension. In fact, the human being is not 3 dimension, it's 2.6 something. It's what we call factoid dimension. Okay. The reason why we have this factoid phenomenon, one is because we have in-between dimension. Again, you can see it is a very, very, what should I say? It's very familiar, right? Because again, first logic. Not exact. We can have something between 2 or 3. But against fractal is using the patterns to calculate the proportion. So you can see for I equal to 1 is a triangle, for I equal to 2 will become a star, and when it becomes higher and higher, it will become a slow fix. The funny thing is all the scientists, including me, now believe F is no fix. It's generated by that kind of thing. So you can imagine F is no fix must be generated by some very simple crystal particle of waters. So what it looks like. So one important theory is generated from this, okay? Because at the end, it will become this. Remember our theory. When A becomes C, okay, and then you have another thing, you got a C, okay, so that C will probably come from A. So that is our logic behind it. So one may wonder how many natural phenomena can be found in fact, or in fact that many. So many. Okay. So in fact, the snowflake, the your bloodstream, the cloud itself is a kind of factor. Okay. The landscape is very important. Landscape in fact is a factors, and even the galaxy, okay, and the DNA, the tree is a very typical factors, because what I'm saying is you can use a simple formula to generate that tree. So again, if you are using formula to do so, which means that very probable this tree is come from equations. If you think about it, you will know what I'm saying. Even the lightning, curl, and financial pattern, okay, can be generated by a set of equations, which means the whole world can be a simulation, just like a TV game, right? So that's why there's a batch of people, not me, okay, believe that the whole world is a kind of simulation, because it can be simulated by a set of equations. So it can be a sim city, right? Or you can see all. In fact, it's all. So some readers say you have so many examples. Does it mean all? And what I'm saying is, as you can see, it covers many things. Organic and non-organic, or something landscape. Okay. The funny thing is landscape. You can imagine if landscape is many things, because landscape contains some river, contains some tree, plants. Okay, so they're all right. The funny thing, they all can be generated by some equation. That's true nowadays. Because nowadays the computer is so fast, and the calculation itself is not difficult. Okay. So very interesting. Of this quantum theory and some atomic law, okay, which means all the things can be generated by set of equations. So it's not a very non-normal thing, because nowadays there are so many people working on TV games and VR games. They are doing that all the time, okay, and now become so real. Okay, the world they generate, we call this VR, right? So it's not impossible. The whole world we see is just a simulation. Yeah. But it doesn't mean that we don't exist. Okay, right. So think about that. So application of chaos theory and factors in quantum mechanics. So I just give you 2 examples first. Okay, one is the word I will talk about it in the last lecture. In the last lecture, I will tell you how our chaotic neural networks for daily forecasting works. Okay, this model. In fact, this model is a combination of different technologies: chaos theory, neural networks, fuzzy logic and genetic algorithm. Okay, I will use 1 or 2 hours to talk about that. Okay, and in fact, we have many papers to go into detail so that you can take a look. Again, it is very important and very interesting for your project, and also it can be used in your future MPhil or PhD study. Okay. And the second thing is fractals. Fractals, in fact, is also very interesting. Okay, in terms of finance, is you can use it in your programming model. Yeah, the fractal is very friendly. For MT4, it only generates a very simple I fractals. These two patterns, bearish fractal and bullish fractal. The pattern is very simple. It's only using 1, 2, 3, 4, 5 bar to define the pattern. So again, do you remember when we talk about fractals, it generates all the time by some very simple pattern, just like a triangle can become a snowflake. So why not 5 bar can generate very complex pattern? In fact, that idea is come from MIT, some professor years before, and it's quite accurate in some sense. But of course, you have to think how to generate the pattern, right? But it comes from a very simple patterns. And for MT4, they have some very simple application on how to use this pattern, okay, together with some index, what we call the alligator teeth, okay. So which means you can combine this pattern together with some indicators and other technical indicator to do some forecasting to give you the buying and selling signal. Yeah. If you again want to know more, you can click into MT4. The MT4 application or documentation tell you how. But again, it's just the beginning because you have to do some actual simulations in order to make sure your projects can be done on using that kind of factors. Okay, so you can see factors can be very simple, but very powerful. So just to tell yourself that a very complex pattern can be generated by very simple patterns. But because the pattern is so simple that it's not easy for you to find. It's so simple, but it's possible. So that means all the times many students and many scientists spending many hours working on this because it exists. It exists. Okay. So summary. So in this lecture, we talk about another two important AI product, Chaos and Fractal. In fact, they are the same thing. Okay. Chaos will tell you the whole dynamics, although they are simple. But when you choose a particular set of parameters, it will become very chaotic, okay, and highly unthinkable, okay, but deterministic. So it can be used for some very complex problem, like the weather forecast and the financial forecast. And the second thing is we learned today is on the fractals. Is the pattern perspective for chaos. Otherwise, put it like this. And fractals, very simple, very easy. A very simple pattern can generate something very complex, and that complex patterns can be found over the world, even within your body. So what we are saying is, if you can imagine, if your bloodstream, your hair, your skin can be generated by fractal, which means a self-simple equation, which means your whole body can be generated by a self equation, right? So which means can be generated by computers. So that's why we have the simulation theory. If you have the simulation theory, you should be happy because which means everything should be predicted because it's a program. You know what I'm saying? Which means you are an agent inside a program because it is a program. So it is programmable. Because it's programmable, if you are a genius agent within the program, you can predict anything you like, technically, because it is a program. Many people, including me, believe that in some sense. But it doesn't mean, okay, religion doesn't exist, okay, because religion can be another set of equations, in some sense. Okay, and maybe God itself is a set of equation, I don't know. But it can be. But in terms of science, Okay, many people believe, okay, everything and many things can be modeled. But how exact or how correct your model, it depends on how much effort you put on that. But it's deterministic. That's true. That's very true. You can imagine everything is come from A to B to C. So if you are very sure about A, the state, and you know the mechanism, so it's possible for you to predict the future. It's possible, okay, but difficult, of course. But it doesn't mean that impossible, because in the old days, when we have statistics, people believe it is impossible because they believe all are random. Okay, so all the time there are two kinds of thinking, either statistic or deterministic chaos or uncertainty principle. Okay, but you can be beaten. Okay, so today we end it here, and next week we talk about another favorite topics on new oscillator. Okay, that is very groundbreaking because it will tell you a whole different way to see the world, a world of oscillators. And when I'm now writing a book on AI, and also that chapter for me is very important because that's true. The whole world is oscillating. Okay, and of course I will tell you how that kind of theory can put into finance. That is the major topics. Okay, so we never leave the topics because, but the topics behind is many very new technologies that can be applied not only on finance, of course, on to many things. But as I was saying, if it can be applied to forecasting weather or forecasting finance, it can be used in many places. Okay, it can be used in many places. So we stop here, and let's continue the lecture in next week. And again, remember to put more effort on your group project and also your term papers. If you have any problem on your project paper, you can make an appointment with me. We can have some Zoom or Tencent WeChat, okay, face to face, to talk about your project or your term paper. No problem. Okay, just WeChat me and make an appointment with me. Okay, thank you. See you next week.